Good afternoon, everyone. My name is Gaurav Singh, and today we'll be learning all about TLS. So, what is TLS? Why do we even need TLS? And what the past, present, and the future of TLS looks like? Okay. So, before we get to that, a little bit about myself. I'm a senior software engineer at miniOrange with some extensive experience of building a scalable web application. At the core, I would like to say I'm a good mix of engineer and a gamer. All right, with that aside, let's set the today's agenda. So first of all, today we'll be setting up the basic instruction or the basic introduction of HTTP and HTTPS. Then we will see what is TLS, where does TLS comes into picture, and then we will compare the different versions of TLS. Lastly, we'll see regarding the future of TLS. Okay. So what is HTTP? Well, HTTP is basically Hypertext Transfer Protocol, but in more simpler terms, it's the language using which your browser communicates with the website or a web server. Whenever you hit, let's say, google.com on your browser, something happens between a browser and the web server, okay? A packet of data is sent from your browser to the server. And going forward, throughout this session, we'll be using the term client as your browser and the server as the website, okay? Website server. So the main problem of HTTP is that it is completely plain text. That means anyone that is basically not monitoring your network traffic, they can see what data you are sending between the client and the server. As an example here, I'm sure it's not very visible, but I'm using a Burpsuit here and I'm basically trying to log in on a HTTP website. On the left bottom corner, you will be able to see my username and password. Okay, so similarly, if anyone is trying to access any website, let's say entering credit card information or credentials in any website that is running on HTTP, it is very, very insecure. Anyone can access it or even modify it. Why can they modify it? Because the client, the browser, has no way of knowing if the response is being received from the server or any malicious actor. All right. Now, this is where HTTPS comes into picture. So HTTPS is basically HTTP over TLS and SSL. It provides a layer of security that is built over three strong pillars. First is encryption, second data integrity, and last is authentication. With encryption, the data is no more in plain text. It is in ciphertext. That means anyone monitoring your traffic, they cannot read it. Even they will monitor your traffic, they will see some gibberish string. Okay, they won't be able to make any sense out of it. Data integrity means anyone, whether it's the browser or the server, when they receive the data, they would be able to know that yes, the sender is the correct one. It was not modified by anyone in between. Okay. Authentication basically verifies that the response that I received was from actual server. The server is indeed who is saying it is. So authentication is mainly done with an entity called as CA, the Certificate Authority. Okay, it is basically a globally recognized organization that will tell, let's say, google.com is actually google.com and no malicious actor. Okay, so when you will try to access any HTTPS page, that is, so nowadays all the pages have moved to HTTPS. So you will see a padlock icon. This will tell you that the website is secure and no one can basically read what you are sending between the browser and the server. Okay, so this is possible because of TLS. So what is TLS? Next, we'll look into that. So the concept of HTTPS everything was started back in 1990s. Okay, with the invention of something called as SSL, Secure Sockets Layer. It was developed by a company called as Netscape in 1994, I guess. So, and over the period of years, it was modified and improved. So there came SSL 1.0, 2.0, and 3.0. After that, it was further improved to TLS 1.0. So why this change of name? Well, around 1999, SSL, the whole project SSL was taken over by something called as IETF, Internet Engineering Task Force. So they changed the name to TLS and made some improvement to it. Okay. So we will go through each TLS version 1.0, 1.2 and 1.3. If you'll notice, I haven't included TLS 1.1. Well, that's because TLS 1.1 is basically TLS 1.0 with very minor improvements, introduction of CBC cipher. Okay, that's why I'm not covering it today. So let's see the past, TLS 1.0. It has some innovation at that time, but right now it is very insecure. But it had innovations such as it introduced the handshake protocol for negotiating the certificates. Why is the handshake protocol required? Consider that with encryption, you are locking something, okay? No one can access the data. That means there should be a key as well. The key should not be available to everyone. Otherwise, anyone can access and basically decrypt the data. So using this handshake process, the server shares the key to the client, and then the client will be able to get what the server is trying to say in the data. Okay. Then there came MAC protocol as well for message integrity, for making sure the message wasn't modified in between. Okay. It has some limitations indeed, such as weak cipher. So MD5 hash and RC4, these were weak, and it was vulnerable to downgrade attack. We'll see what is a downgrade attack later on. So due to downgrade attack, it was also vulnerable to Poodle. Now, Poodle is a padding oracle attack. I won't go too much deep into what is a padding oracle, but it's just that the data that you are sending from the client to the server, it is form of bytes. Okay, so let's say it's a bit stream. So let's say each byte is made of 8 bits. Okay, and let's say the whole message is some number of bits, but at the end only 5 bits were occupied for the last bit. So 3 bits are still empty. But the data needs to be sent in form of bytes. So the 3 remaining bits were padded. Okay, were padded with any random data. All right. So using this Poodle attack, the oracle using the padding oracle method basically. The attacker basically identifies what bits would be padded, and they will try to initiate the attack from there. Second limitation was it lacked forward secrecy. What is forward secrecy? The whole encryption works with, as I mentioned, keys. Okay, if let's say the key got stolen, then all your past session data will get stolen as well. That's basically happen when something lacks forward secrecy. Because of all these reasons, TLS 1.0 was deprecated in 2021, and it is now in the past. I mentioned something called as downgrade attacks earlier. So let's look at what is a downgrade attack. Let's say the browser is making a request to a website that is using TLS 1.0, and there is an attacker in between which is doing MITM, man in the middle attack. In the downgrade attack, what it will do, it will send repeated failed requests to the website. Okay. Now the website, when it receives multiple failed requests, it will think that the browser doesn't support TLS 1.0. So it will downgrade its version to SSL 3.0. See, at that time, TLS 1.0 was new. So mostly all of the websites had to support the older version as well. So just like even right now, websites are supporting TLS 1.3, but they do also support TLS 1.2. Okay. So using this downgrade attack method, the website changed its protocol to SSL 3.0, and since SSL 3.0 was susceptible to Poodle attack, the attacker can basically use that. All right, so this is what downgrade attack is. That's why we invented, or IETF invented TLS 1.2. It provided stronger encryption methods such as AES, HMAC. Then it had optional forward secrecy. So forward secrecy was introduced, but it was still optional. It was possible using DHE and ECDHE, so develop help an algorithm. And it also provided an option for flexible cipher suite. So what is a cipher suite? Consider it as a bag in which you have multiple algorithms that you support. So let's say I'm a browser. I'm saying that I have this bag. I am supporting this algorithm. You can use any of the one that you want. So this was introduced in TLS 1.2. We will see some limitation as well going forward with this presentation. So limitations are, it has a complex handshake system. So the handshake is secure, but it is still complex. then it is also vulnerable to attacks like Beast. Beast is not directly linked to TLS 1.2, it was linked to TLS 1.1, but TLS 1.2 was still susceptible to downgrade attacks. So similar to what I explained you earlier, attackers can basically convince the server to switch to TLS 1.2 and perform Beast attack. Another attack it was susceptible to was Lucky 13. Lucky 13 was the Lucky 13 comes into picture when you are using CBC cipher for key exchange. Okay, in that case, if there is a misconfiguration in the defense mechanism of CBC, you can perform Lucky 13 there. Again, we won't be going too much into the specific attack for this session. So I have written that this is the past and the present. That's because it was introduced in 2008 and many websites have moved now to 1.3, but many of them still supports 1.2 as well. Okay, so we will go to something called as handshake. So as I mentioned earlier, handshake is something that is required for exchanging the certificates so that both the client and the server, they can exchange the ciphertext. They can understand the ciphertext, and only they will be able to decrypt it, no one else. That's why the handshake is important. So in this example, I have taken, let's say, Chrome browser, that is the client, and let's say LinkedIn website, the server. So in this process, the very first step is called as client hello. So the client sends a message to the server, and in this message, client sends three things. First, the supported TLS version that it has, cipher suits that support, and a client random. I have explained cipher suits, but what is the client random and why is it needed? In cryptography, you must have heard about the concept of salting. Salt is basically used to add a randomness to your encryption algorithm, so that even if someone got your keys and they know which algorithm you are using, they won't be able to get the plain text out of it. That's why the salt is necessary. So the client random basically acts as the salt here. So these three things are sent to the server, and then server also sends its own server hello. And within that server hello, it has the certificate, the SSL or TLS certificate, its chosen cipher suit. So as I mentioned, the cipher suits is basically a bag of all the algorithms that the client supports. So being a server, I chose one of it, okay, based on whatever my requirement is or whatever my program is. Okay, so I have chosen a cipher suit as a server, then I will also add my own salt to it. So I have added my server random as well. So client hello and server hello is done. Upon receiving these three things, what the client will do, it will first of all verify the SSL certificate using the CA that I mentioned earlier. Using that, the client will, or the browser will understand, yes, this certificate is indeed of LinkedIn and no other party. Then it will generate something called as pre-master secret that is encrypted with the server's public key. This is required so that, why the server's public key? Because you see, this is performing asymmetric encryption. So server has its private key and it is sending its public key. It is telling the client, you will send me any encrypted data. I will try to decrypt it with my private. If it's successful, then yes, I will consider that you got my certificate and you have verified it at your end. So pre-master secret is sent to the server from the client, and the server will basically decrypt it using its own private key. After this step, both the client and server, they will generate a session key using three parameters: client random, server random, and the pre-master. So at this point, both the client and server has these three details using the previous steps that we performed. Okay, so obviously, since they are using the same parameters, and they will be basically getting the same results for the session key. And going forward, the client send a finished message that is encrypted with the session key, and it will send a client ready message, and the server will also send a finished message that is again encrypted with the session key. Will send a server ready message. So going forward, within this session that is created, all the message will be encrypted using this session key. In this case, the key is same. So this is symmetric encryption, right? So the whole TLS 1.2 handshake incorporates asymmetric encryption for exchange of keys, then the symmetric encryption for generating the session key and encrypting the whole communication data. So there were a lot of steps, and that's why there are some limitation of 1.2 as well. So it supports RSA key exchange, which basically lacks forward secrecy. And the method I told you just right now, it was based on RSA. So it doesn't support forward secrecy. That means that if the certificate got stolen, all your previous communication data is out in the open. Anyone can decrypt it. And this handshake is obviously slower because of so many steps. And it is vulnerable to attacks on decrypted algorithms. So there are, since TLS 1.2, it has a wide range of cipher suit. It also has some decrypted algorithms as well that were vulnerable. Okay. Now this is where TLS 1.3 comes into picture. This is the present and the future. For now, we will see more future ideas that could be done in TLS. But for now, let's consider it as the present and the future. This is the current standard that is being supported by many applications, by I think all the websites, and in addition to some backward compatibility with TLS 1.2. So it provides a very faster and simplified handshake. We'll look into that in a moment. It also encrypts the handshake process for better protection. It only supports modern ciphers that are not vulnerable or known vulnerable, such as AES GCM or JACHA 20 or Poly 1305. The forward secrecy is now mandatory using the use of DHE or ECDHE key exchange. So what happens in DHE? Basically, the session key that we look just right now, that is being generated for every session. So this is just a temporary session key in DHE algorithm. That's why it provides forward secrecy. Even if your certificate got stolen, all your previous data was done using a different session key. That's why it cannot be decrypted, right? So because of all this reason, there are some benefits like enhanced security, reduced latency, and future-proof design. Kind of, we'll see why. Then let's look at its handshake. So client hello, first of all, client will send its protocol version, which will be 1.3, list of cipher suits again, client random, and one another thing, some parameters for calculating pre-master secrets. Let's say we are using DHE, so it will share its own key share, something called as key share for the DHE. So for the DHE algorithm, client will need to have its own key share, and the server will also need to have its own. So all the first three parameters are same as TLS 1.2, but at the end, it also provides a pre-master secrets parameter. So this is for client hello. Now server, at this point, it will generate its own random, and it will generate the master secret based on the values it got. Because server has its own key share, right? And once it received the key share from the client as well, it will generate the master secret. Then it will send the server hello and finish. Just that's it. So no more back and forth. Server received the client hello from the browser. It will send these data in the server hello. So first is the server certificate, a signature, digital signature. Signature is required. Basically, let's say you have a letter. At the end, you are making a sign. Okay. Whoever receives this letter, based on their signature, they will understand that yes, this message was sent by this person. Similarly, the signature will tell the client that this whole server hello was sent by LinkedIn or whoever the server is. Okay, that's why the signature is important. And if anyone, let's say, modified the signature, client has a way to identify that the signature was tampered, and if it was, I will just discard that message. Okay, so there is digital signature, and then the server will also include its random and chosen cipher suit, and finally it will send a finish message. Upon receiving this, first of all, client will verify the certificate and signature. Okay, same using CA, and it will just verify the signature hash if it matches. The thing about signature, digital signature, is that if you change anything in the data, even one character, the whole signature gets modified. Okay, so using the certificate, the client will be able to verify yes, the signature data is correct. Then it will also generate the master key, because at this point it got the key share from the server as well. So it will generate its master secret and send a finish message. That's it. Now using this master secret, they will use it as the session key and perform the all communication. So that was it. Just 3 simple steps for TLS 1.3 handshake. It provides perfect forward secrecy. Perfect forward secrecy, as I mentioned, even if the certificate got stolen, the session key would be different for all the past communication. So your past communication are not hampered. Okay. Obviously, the round trips are less, so the handshake is faster, and it removes legacy algorithms such as RSA for the key exchange. All right. So there are so many different versions of TLS, but who is using what, and over the period of time how it has evolved. Okay, so I have drawn a graph here. So left side is basically or y-axis is basically the percentage of websites that we're using that particular version. So the light blue color is TLS 1.0, middle one is 1.2, and the darker one is TLS 1.3. Okay, starting from 2008, we'll see Google was using TLS 1.0 in 2008. Then at around 2011 or 12, it moved to TLS 1.2, started moving to it. And then at 2018 or 2019, it moved to TLS 1.3. Well, at least for some of its services like Gmail. Then around at 2022, it moved all its services to TLS 1.3. Similarly, the same trend is for other organizations as well, such as Apple, Facebook, AWS. They were using TLS 1.0 in 2010 or 2011. Then they slowly moved to TLS 1.2 over the years as the older encryption got decrypted, and they needed to basically use the latest version of TLS, and again they moved to TLS 1.3 in 2020 and 2021. Okay. So this is basically the a graph of basically how the companies were using TLS version over the period of year. But if you are accessing a website, how will you be able to identify which TLS version it is using? It's pretty straightforward. Just go to any website. Again, it is not very visible. But if you do inspect element using F12 or just right click on it and press inspect element and go to the security tab, you will see something called as the page is using HTTPS, and under the connection section, it is at the last, you will show the TLS version as well. So if it's using 1.3, you will see that. You can also see the certificate. This certificate is the public certificate that was provided to the browser, not its private key, obviously. So this is basically complete about what we are doing right now with TLS. But what does the future of TLS looks like for us? I have written a few points based on my understanding what could be the future of TLS. So first is obviously mandatory adoption of TLS 1.3. If there are any website they were still using 1.2 or older version, they need to move to TLS 1.3. Shorter lifespan of TLS certificate. So with every certificate, there is something called as its lifespan or its expiry date. Right now, the maximum valid expiry date for any TLS certificate is 13 months or 398 days. Okay, you cannot have anything above that for a website's TLS certificate. There have been some requests from Apple and Google to even reduce it to 45 or 90 days. It's still an ongoing process, but yes, this could be done in the very near future. Then increased use of mutual TLS. So mutual TLS is basically what we saw right now was one-side TLS. Only server certificate was authenticated by the client, but there was no client certificate that needs to be authenticated to the server. So any browser can make the request. With mutual TLS, the authentication is done from both sides. That's why it's called mutual TLS. So from both, and you must have attended a session yesterday as well regarding it. It had some overhead because now there is an additional step of validating the client certificate as well. So the performance would be affected indeed. So maybe we would be able to mitigate that problem and include it as a generic standard as well. Then there is something called as encrypted hello. Encrypted client hello is basically, it works on something called as DNS over HTTPS. All right. So what is DNS? Whenever you are accessing a URL, let's say google.com, there is a physical address behind it. Okay. So there is a DNS lookup happening when you type google.com on your browser. So it will fetch the IP address that is linked to this google.com or any website, and it will send back the IP address to the client to make the request, because the data needs to come from a physical server. Now this DNS lookup is open. It is not encrypted, but DNS over HTTPS basically encrypt that as well. And it uses the same principle to perform encrypted client hello. In the handshake, we saw the first step was client hello. Using the same method, we can encrypt the client hello as well, so that any attacker, they won't be able to identify what the client is trying to do. If they are, let's say, making some payment or anything like that. Okay. Then there is something called as post-quantum cryptography for TLS. In yesterday's keynote, there was a brief talk about quantum computing. Well, you can consider quantum computing as future of computing. It is something called as, let's say, it's a very powerful computer that is even able to break the current cryptography or the current encryption methods. So even if you are using DHE or ECDH for client exchange, or let's say AES for encryption, it can be broken using cloud computing, using quantum computing, sorry. So once that has been introduced and available to the general public, obviously attacker will use it for their own good. So we need some, from the defense side as well, we need some cryptographic mechanism that will basically challenge the quantum computing as well. All right. So yeah, this is basically the future of TLS. This is basically the future of TLS based on me. If you have any questions, or if you think what could be the future of TLS, we can discuss. Or yeah, please go ahead.
What is the reason to release the lifespan?
Yes, definitely. No, not in a single year. So right now the renewal is happening single year, because the lifespan is like that. Lifespan is 13 months. So the lifespan of the certificate, this is a long time certificate. If it gets, let's say, stolen, any future communication, whoever the attacker is, they can use the certificate for its own good. So to basically dampen the effect of it, we are reducing it. But then you will ask that why not just reduce it to 1 hour or so. But then, well, if you reduce it to something like 1 hour, the handshake will need to happen every hour. And that will that will have performance impact as well. That's why, to reduce the impact of it, we are changing it to 45 days or 90 days. Because that is not the only layer of security. That is just one of them. Another one is, let's say, the session key that I mentioned. Session key is generating for every session, even if you are using the same certificate.
Because security is more rely on that certificate.
Exactly. Actually. Yeah, that's correct. But that's not the only thing. Right now it is for, let's say, a year. And even if we change it for 3 months, we need to renew it after 3 months. Right. So within that lifespan, let's say it got stolen. Okay. So your application will be affected for 3 months only. Earlier it was a year. So,
but this is again overburden for the IT.
Right. It will be overburden. So that's why now there are process of automating the modification of certificates. I think Let's Encrypt provides an automation for this.
Okay.
Thank you. Anyone else have any question? You can also leave me a feedback by scanning this.
Yeah. So I think last year Google Chrome mandated 90 days of TLS certificate expiry.
Yeah.
And I think at that time there was a huge rush overall in the PKI team.
Right.
Because maximum time it's the Chrome only that is used while using these websites.
Yes.
And it was a big headache for getting these renewed. I think it was thousands of them, and for organizations across worldwide, there wasn't an automation system. So they had to invent their own scripts and all to handle it, right? Yeah, I wanted to add.
Yes, absolutely. So this will again generate a problem that needs to be solved by a proper automation solution. Okay. Yes. Thank you. Anyone else? Okay. Thank you, everyone. Thank you for your time today.